Well, welcome back, everybody, for part two of Irrigate Better in BC's Kootenays and Kootenay Boundary. Uh, if you didn't join us last time, we've got a YouTube up of the last session, the irrigation anatomy, where we went A to Z and really checked out all the different parts and pieces. Today, we're really going to start putting that all together. Before we do, I just want to thank a few people, particularly Bruce for being here with us tonight. And also all of our funders. The Climate and Agriculture Initiative BC is really spearheading this, funding from the Columbia Basin Trust. And I am an advisor with the Kootenay and Boundary Farm Advisors, and I'll tell you more about that at the end. But if you are a farm in the Kootenay and Boundary regions, we're a free service. We offer consultations with experts, farm visits. We do lots of workshops such as this. Field days are our favorite thing. And you can call us anytime and we can put you in touch with experts like Bruce. Again, funding from the Columbia Basin Trust and all kinds of other partners that you can see down below. So I would also like to thank Andrew Peterson from the Ministry of Agriculture and Ted Vandergulik, who's now the president of the Partnership for Water Sustainability. Both of them water gurus in their own right, and they've contributed a lot of excellent material that we'll be using tonight. I'd have to say that the Irrigate Better is the name of the series, but another name for it would be Save Time, Save Money, and Grow More. That's really what we're after here. We want to be able to produce better crops for less money with less time and using water more effectively. The plan is the same as usual. We're going to go for a half hour, maybe 45 minutes tonight with Bruce, and then there's going to be a question and answer period afterwards. Today we're really focusing on pipe design, sizing main lines, sizing your whole system, laying out laterals, and thinking really carefully about hydraulics, how pipes work, how water flows in pipes, and the considerations you have to make sure that you can get a uniform distribution of water, which is what we're going to cover in the next session when we look at sprinklers and drip emitters and try and think about how to get that water evenly spread across your field. I'm going to make one caveat before I hand it over here to Bruce. There's a lot of complexity in tonight's presentation. There's a lot of tables, a lot of numbers. We've tried to simplify it, but there's really no simplification of some of these concepts. So if you're having any trouble at all, please don't worry. Probably lots of other people are in the same boat, and don't hesitate to ask a question or ask for clarification on any of these. And Bruce is going to really walk us through it one step at a time. So over to you, Bruce. Thanks very much again for being with us tonight.
Thank you very much. Thank you, Andrew. So today's topic is about sizing of lines. It's actually sizing of all of the apparatus that you would need when you are planning your irrigation system. Obviously, your pipe sizes are one of the most relevant of these things, but we're going to discuss a lot of the different parts of your irrigation system that you should have be making some decisions on size and some of the various characteristics that you would require. Next slide, please. Okay, if you were with us on the first one, you did see this picture. This is an anatomy of an irrigation system. It's a good overview of the system. And so there's a lot of different parts, as you can see, on the irrigation system. We have everything at our point of connection. I mean, obviously, if you're at a pumping system, you have to have some thought into the size of the pump that you have, and that pump cannot exceed what you have available, obviously. And from that, you're going to trunk into your main line of your system. And your main line is one of the primary things that we're going to be discussing today. What is the size of the main line that you're going to have? What is the type of material of the main line that you will be using? Obviously, the fittings that go along with it. And following that, we will be looking at the lateral piping, which also has to be sized. So this is, we have discussed BC Agricultural Water Calculator. And one of the things that we obviously have to know is what are your water needs for your whole farm. If you go to this calculator, BC Ag Water Calculator, you're going to be able to go in there and you're going to be able to dial in what specific crop you have, what area you are in, the amount of acreage that piece of property has, and from there you can change it to the amount of area that you in fact want to irrigate. From that, you're going to get a water demand, which is going to tell you what your water requirement for the course of the season is going to be, 2,080 cubic meters as it shows here. It's going to tell you that your peak flow demand, the area that we were looking at here, I believe was Creston. Oh, yeah, it says at the top. And the peak ET for that area is 5.5 millimeters or 0.22 inches per day. So that's the parameters. So that's the amount of volume that we're going to need for water, 5.5 gallons per minute per acre. So if, depending on the size of the acreage that you have, you would multiply that. If you had 10 acres, you would be allowed 55 gallons per minute of water. We also want to look at various other things besides the size of the field. We're going to look at what your crop is. Obviously, various crops have various water requirements. And we want to be looking at the ability for you to be able to change crops and still have enough water to facilitate being able to irrigate it. Climate change obviously has an impact, and we want to talk about future expansions and how that will impact you too. Next slide. Okay, long-term thinking. Here's a real simple diagram that gives you an idea of what I was talking about. Okay, so this particular acreage here is 10 acres. Presently, this grower has determined that he only wants to irrigate 5 acres of that parcel. But he has 10 acres. And he has 10 acres of water available too. That could be from a purveyor, that could be from his pump system, but he has the capability of having enough water for 10 acres. So on the slide before, we had the factor of a 5.5 gallons per minute per acre. On that 10 acres, he would be allowed 55 gallons per minute of water. If he's only going to be irrigating 5 acres, then he's only going to be requiring half of that amount of water, or 27.5 gallons per minute. So one of the first things that you have to do is you have to have some long-term thinking on this. We want to talk about, if you have 10 acres of water available, and in your mind you don't think you'll ever exceed the 5, is it a wise idea to just size that mainline for the 27.5 gallons per minute? Or should you keep in mind the 55? Even though pipe has gone up significantly in the last little while because of our world situation, pipe is still relatively inexpensive in the scope of things. So the difference between, in this case, a 2.5 or a 2-inch pipe versus an 1.5-inch pipe is not that significant. And the long-term value of increasing that size is going to be well worth your while. You'll thank yourself someday way down the road. Obviously, we have to look at elevations, distances that you're running. All of those things are going to have an impact on the size of the piping that you have. Next slide, please. Okay, now here's getting it into a little bit more detail of a plan. You can get a detailed plan like this, which will even maybe break down your soil types into the various areas there. We're going to look at various types of systems. This one here is looking at a lot of potential for wheel moves and the likes of that. So you have a large property. You want to look at all the different types of equipment that you will be needing in the different areas, and drawing it in there. And even if you're not going to do it right away, you want to have the capabilities of having that pipe for the right size piping for those areas. So the complexity in a situation like this one here is you are going to have to look at wherever your water source is coming from, and how many acres maximum you're going to irrigate. The next thing you're going to look at is, are you going to be irrigating in a lot of different areas at one given time, or is all the water going to go to one specific point? So in other words, in this big picture here, if we had 100 acres of land here and we were using that 5.5 per acre, you would have 550 gallons per minute of water. Well, the size of the piping that you would require to have that 550 gallons per minute at the very end of the field would have to be large enough to facilitate that. So we would be talking about an 8-inch main line in order to get the water to that point. However, if you were feeding from a given location and then you split and you were using half the water on either side of this, and that then you would be able to reduce the size of that, and you may be using some 6 and 4-inch piping, for example. A lot of this has to be looked at. We have to do a lot of calculations. Elevations are very important, and all pieces of property are all not tabletop flat. Elevations can be challenging. If you have large rises in elevation in one area, you may need more pressure at that particular spot than you would in another area that's dropping or at a level keel. So we like to see a map with all of the contours graphed on it. You can get that from Google, or there are a lot of different areas you can get that. In my particular areas, a lot of times I have an altimeter and I'll go out and I'll measure my elevations to the various areas there to calculate this all out. But that's a very necessary step in mapping. Next slide, please. Okay, here's some of the things that I was talking about. I was talking about the type of piping that you'd be using. So there's some selection. So when you're going to make up your mind on a type of piping that you would require, there are some specific things that we have to look at. We want to look at how do you size pipe. You size pipe based on the volume of water you have and the volume of water that can pass through a given size of pipe. Engineering specifications on a majority of piping that we have should not exceed 5 feet per second. Why? When you exceed 5 feet per second of volume going through a pipe, you are going to create a situation where if you've heard of water hammer or water surging, those things occur when water changes direction. When water is going in one direction, when a valve closes quickly, it can go back 2.5 times as fast in the other direction. And so with that in mind, we want to keep our velocities under 5 feet per second. So there are charts that we will bore you with a little bit, which show you what your various velocities are in the piping, but that's going to be our governor to determine the size of the piping that we're going to use. Obviously, you have friction loss in that pipe. The friction loss that's there is caused by the water movement through that pipe. So obviously the diameter of the pipe and the type of pipe are important. There is on old slide rules, when I started out in this business, we used slide rules, and we had to dial into that the coefficient of roughness of the pipe. So obviously, if you had an old steel pipe, perhaps rusted in that, the water is not going to be able to flow all that smoothly through it. Compare that to modern day polyethylene pipe, PVC pipe, high density polyethylene, and the water flow is going to be a lot smoother through it. Hence, there'll be less friction loss through that type of piping. And actually, so that a smaller pipe can actually deliver more water in certain circumstances, as long as your velocity does not exceed that 5 feet. An example of the inner diameter of a pipe on a 1-inch piece of PVC pipe, if you were flowing through 10 gallons per minute of water through it, that's a schedule 40, I think, by looking at that, you have a velocity of 4 feet per second and a pressure loss of 3 pounds per 100 feet. You'll see that on a chart in a few slides. If you were to go to 20 gallons per minute, your velocity is 8 feet per second. So therefore, you should be looking at upsizing your pipe to maybe 1.25 inches because of that velocity. You're losing 11 pounds versus the 3 at the 10 gallons per minute too. Next slide. Now you're going to see pressure ratings. All piping have pressure ratings. It gets confusing on PVC pipe, for example, because you can buy anything from a class 63 pound, which you don't see. That's usually just for water transfer in a very low situation. Your wall thickness is very minimal. To a class 125, 160, and 200. For the difference in pricing, a majority of piping that we use today would be of the class 200 variety. In days past, people used to use class 125 and 160, but the difference in cost for that extra bit of meat that you're going to get in a class 200 pipe warrants keeping it that way. The burst pressure, which is important because you shouldn't be anywhere near it, you can see burst pressures on that pipe. So if a pipe is rated at 200 pounds of pressure, it's going to have a minimum of 1.5 to 2 times that before it'll burst. But we don't want to ever get into that situation. So class 200 pipe, you can know that it can safely operate up to 200 psi, but keep in mind that water hammer. So if it's 2.5 times going back the other way, your 200 pounds of pressure would be over 400. So keep that in mind. Schedule 40s and Schedule 80s are different. They don't have a pressure rating. A lot of Schedule 40s and 80s do have the pressures, but what you're going to find is that as you increase your size of your Schedule 40 and 80 pipe, the wall thicknesses stays standard. It's an old rating system that rated steel pipes, and in the transition to PVCs, the Schedule 40s and 80s had to maintain a certain wall thickness at a given size, and so that's how the schedules are there. Schedule 40 pipe, for example, has a lot higher pressure rating than a class 200 pipe up to 6-inch. When it gets to 6-inch, your standard wall thickness is such that 6-inch Schedule 40 has less pressure available than class 200 pipe. SDR, standard dimension ratio, that's something you're going to see on a pipe. For example, a class 160 pipe has a standard dimension ratio of 160. Class 200 pipe has a SDR of 21, and it's arrived at by taking the outside diameter of the pipe divided by the thickness of it. Pipe cost is very relevant to the weight. So the thicker the wall, the more expensive that pipe is going to be. You should always keep in mind the ability, as I was talking about with the surges and water hammers, if you're in a situation where you're going to be consistently having this surging, you should be doing something about that, but also you should be looking at the sizing of your pumping to buffer that surging that you're going to have, so you're not going to have a lot of broken pipes prematurely. Next slide, please. Okay, so the water hammer that we're talking about. So how does that happen? When a valve closes too quickly. In a lot of electric systems, there are relatively fast closing valves. There are ways around it. You can get some valves that are slower closing, but inherently, an electric valve is going to be a lot quicker closing than, say, a gate valve or a ball valve. Ball valves actually, on a main shutoff, I do caution people about using them because a lot of people think it's awesome that you just got to quickly turn a big handle and your water's on and off. But you're creating a water hammer by doing such. And I've seen pipes blow apart very quickly by doing that in high pressure situations. Water rebounds fast, 2.44 to 2.5 times. So here you can depict that where you show the valve open, and depending on how quickly you close that valve is going to create a water hammer. So a valve on a mainline, an isolation manual valve, there are some benefits to having to turn a handle on a gate valve because it's going to be a lot slower closing valve. If you're using a valve to throttle, and I did go over this at other times, gate valves should not be throttled. Why? Because a gate valve throttled is going to prematurely wear your seat out on your valve, especially if you have some turbidity in your water, you have some sand and grit. It's going to break down your seat. When a seat goes in a valve, you could change all the gates you want to, but it's still not going to shut properly. If you want to throttle a valve, best valve for that is a globe valve. The ball valve will work for throttling, but the globe is the one that is specific for that purpose. Excuse me. If you have nothing else you can do about water hammering and surging in a system, quick reacting relief valves are the way to go. A quick reacting relief valve with a pilot is going to sense that change in pressure, and it will relieve that pressure. A good example of where in an agricultural situation where you could use a relief valve is if you have a pump system and let's say it's a submersible pump, so it can climb up in the pressure if you don't have very little water running. You're going to have to shut your pump down every time you want to change your wheel moves. unless you have a method of getting rid of that water. One option is to have a relief valve on there, so as you close valves down, you're going to be able to relieve, hopefully back into your water supply, wherever that is, be it a reservoir, be it a creek or whatever, so that can happen without you having to shut your pump off. So it can save you some time. You can get some other arresters that are shown on here. They go online, and it's going to just take the buffer of that. In the irrigation systems, you don't often see them. They're in smaller systems a lot of time, in basements, houses, and the likes of that. Okay, next slide. Just some other items that I wanted to talk about a little bit on a main line. We've discussed a lot about air relief valves, and it's only over the last 20 years or so that air relief valves have been consistently put into irrigation systems. Prior to that, they weren't put in, and there was a lot of damaged pipes that were created by the air that had built up in the pipes. Every high point as you change your elevations, you should have an air relief valve on a system, and every 1,000 feet rule of thumb is a good idea to have a relief valve or an air release valve. Drain valves on the low points of your main line are going to ensure that your water is going to evacuate out at those points. Any lower pockets where water has, even if you drain it, water can collect in those points. And if there's more than half of that pipe is full of water at that low point, it's going to break. So that's a great place to split a drain. Drain valves, if they're really deep down on the ground, you need a method to get on it. The one on the left is an expensive valve. It's a T-handle valve, but you can get a curb rod that goes onto that, so they're a lot easier to get at, to use as a drain valve. A gate valve, you can make a very simple two-prong type of a key that'll open those under deeper applications. Ball valves, it's a little bit more of a challenge. I wanted to talk to you a little bit about pipe burial. If you have a rocky situation, it's always a good idea to have a sand bed. And I talk about a sand bed underneath of your pipe. It's excellent. You want to, get rid of all of the larger rocks and that are there. Give your your pipe a good bed of sand underneath it. And then even if you were to put sand on the top of it, that's got two very big benefits for you. If you're running some heavy traffic over the piping, some big tractors and the likes of that, if you don't have good sand bedding on it, compacted properly, you're likely going to maybe cause a problem with breakage. Depth of burial is important. I recommend at least 2 feet of burial on a main line. But the other advantage of putting sand on a pipe, and I've seen it a lot in the last little while, is that people who do that and sand bed your pipe, you're taking a lot of care. You're going to probably get a lot longer life out of that system. But also, when you go to do a repair, as soon as you hit sand, you're close to where your pipe is, and so you're going to be a little bit more cautious. So I think it's an excellent method of going about it. Next slide, please. Okay, I talked about boring you with some friction loss charts. Here's how we're going to determine the size of this piping system. So it's the Farm and Creston still. It's 10 acres. It's got 5.5 gallons per minute per acre allotment. So it's 55 gallons per minute is the amount of water that we're going to be sizing their piping system up. If you were to look at this chart, a 2-inch pipe. Now you have to be very. This is where it's going to get a little bit confusing. I suggested to you that in piping on a main line, I would recommend a class 200 or a schedule 40 pipe. A 160 could be acceptable if you had 100 pounds of pressure, but I would still probably recommend going to 200-pound pipe. Based on that, the wall thickness on a schedule 40 pipe, now keep in mind your OD, your outside diameter of all PVC pipes, and HDPE pipes are always consistent. So a 2-inch pipe, for example, has, I believe it's 2.38 inches OD, and that's consistent. But what changes is your inside diameter. So, for example, that class 160 or class 200 pipe, the wall thickness is going to be substantially less than a schedule 40 or up to a schedule 80 pipe. So the thicker the wall, your outside diameter stays the same. It means your inside diameter is going to get smaller. You have a smaller inside diameter. What that means is that the velocity, because the size of the opening is smaller in a Schedule 40 pipe, so the velocity of the water flowing through there is going to be higher. So we have this rule of 5 feet per second. It gets confusing, but the 5 feet per second of velocity that you have there is going to be, you're going to be able to flow a little bit more water in a Class 200 pipe than you would in a Schedule 40 up to 6 inches. Keep that in mind. In this case here, we've elected to go to a 2.5-inch pipe. Why? Because it's crucial. We don't want to have water hammer. Your velocity in your 2-inch pipe, if we're looking at Schedule 40, is marginally, I think, I don't have this chart right in front of me, but it's probably about 5.2 or something like that. Some people would think that would be acceptable, but it is a little bit more. It would be about, say, about a 5.2 on a Schedule 40. If you went to a Class 200 in that 2-inch pipe, your velocity would probably be about 4.85, 4.9 in that area. So it would be under your 5 feet per second if we were going to really stick closely to that. So if we were sizing this specifically on the velocity, we would say use a 2.5-inch pipe. But depending on the pressure that you require at the end of your line, and if you're very close to the 5 feet per second, you might look at a Class 200 2-inch pipe, and it would be slightly under. It's going to save you some money and do what you need. But if we're in a situation where we can't afford to lose any pressure, because let's say we need 50 pounds at the end of the line, we have friction loss, maybe we have other losses in fittings and the likes of that, then you might want to go to a larger pipe so that you don't lose that extra pressure. So let's say if you needed 50 pounds of pressure at the end of the line, but you only had 55 to begin with and it's flat or it's going uphill. Well, then if it's going uphill, there's nothing you can do about it. But if it was flat, that you're not going to have, depending on how long that line is, but you may lose more pressure than enough, and so you wouldn't have the 50 pounds of pressure at the end. Hence, you go to the 2.5-inch, and you're able to gain that pressure back. Next slide, please. Yeah, no, this is a myth, and I've heard it a lot. We heard it on our Kootenai trip quite often. And that's the fallacy, the fact that people think if you put your thumb over the end of a piece of hose, you're creating more pressure. You're creating more velocity and water speed, but you're not creating more pressure. The fact is that pressure loss occurs from friction, and the longer the distance you have and the smaller the hose, the more friction you have. If you have a larger piece of pipe, you can have less friction loss. If you have, the volume may not be as fast because it has a larger pipe to travel in, but we're not going to be losing the pressure. So slower water means less friction loss and the same flow and the same pressure. Faster water means more friction loss. You have more friction loss, that's where you have the velocity, like a Venturi effect. And that's why it seems like the pressure is heavier, but it isn't. Thanks. Okay. Now here's, excuse me, I want to go over this. Okay, so here we're sizing out a main line. We have a flow in the main line required of 55 gallons per minute. We need, at that valve, we require 50 pounds of pressure, 49.5 it says here. At the source, we have 60 pounds. So we have 10.5 pounds of pressure variance between the source and our zone valve. The lineal distance of the line that we're going to be putting in is 1,000 feet. We said that in this case, we're going to use a 2.5-inch diameter pipe. And elevation 500, elevation 500. What does that mean? It means that you're in a level terrain. We have 500 feet at each location above sea level, so there's zero rise or drop in elevation. So the next slide is going to look at friction losses. Okay, so at the 55 gallons per minute at our source, over the 1,000 feet, using the 2.5-inch pipe with zero elevation change, we have a friction loss of 0.88 pounds per 100 feet of pipe in 2.5-inch pipe. We had 1,000 feet. So if it was 0.88 per 100 feet times 10, gives you your loss in 1,000 feet. So we're going to lose 8.8 pounds of pressure in that pipe over the 1,000 of distance. Fitting loss, this is 20 to 25% is the maximum people will use it for that. On average, I usually look at a factor of around 15%. It's a gut feeling you have on that, but it's based on the amount of fittings. If you have a whole series of elbows and T's and that on a line, but especially elbows, 90-degree elbows, you have a lot of brass gate valves and that on the line, we might be looking at a 20% fitting factor. But if it's a straight line with very few fittings on it, you might only have a 10 to 15% factor. It's always good to err on the high side. So I would say the 20% is a good judgment figure there. So what we're going to do is we're going to take the 20% of the 8.8 pounds of loss of the main line, and it's going to give you 1.8 pounds of loss. And then and you're going to have your 8.8 pounds that you're losing in that 1,000 feet. So you have a total loss of 10.5 pounds. The velocity of that 2.5-inch pipe at 55 gallons per minute is 3.6, so far under our 5 feet per second. And we're going to have a total friction loss of 10.5 pounds. So in that case there, we would be able to, the 10.5 pounds that we were losing off of that 60 that was there, we were at 49.8 psi. Now we're going to throw another monkey in here. We're going to put some elevation change in here. So over from our source of water to where our zone valve is, we now have a 50-foot rise in elevation. So what does that mean? It means that we're going to have an extra 50 feet of lift that we have to go. So we're going to be losing more pressure because of that extra lift. That extra lift is going to lose it to an extra 22 pounds. And so what that means is that from your source, you would actually need you would have to have 82 pounds in order to give you the 49.8 pounds at your zone valve. How I usually suggest working out friction losses is the same way as we work out when we calculate out the size of pump. We start at our source and we calculate out all our friction losses, all our elevation changes, all of our losses that occur in the line over that distance. And then we determine at the very end of the line, if we're running a wheel move, if we're running a traveling gun, if we're running a solid set sprinkler system, what does that last sprinkler head on that zone require to operate properly? If it's a brass impact sprinkler head, 3/4 inch one, you probably want about 40 pounds of pressure. So what I will determine is from my source to the end, I require how much pressure. So if I start at 40 pounds, I require at the very end, and I work my way back with my friction losses at the beginning of the line, it's telling me what I would require at my source to deliver 40 pounds pressure at the flow that is required for that one sprinkler at the end of the line. Next slide, please. Okay. So here we have various layouts of piping systems that you should have on your irrigation system, how your laterals run. The best, most efficient method of piping a system is equal distribution, feeding from a center point, minimizing the length of your lateral lines. So in example 1, we are feeding from our valve location, and we're feeding 8 sprinkler heads all in a row. That could make a turn and go in a different direction, but we're going to just have one line with all our heads in a row. So we're going to have heads, whatever the flow of each of these heads is going to be. We are going to be, as we go down the line. So at this point here, let's say that those heads were 5 gallons per minute. We would have 5 gallons per minute to number 1, 10 at number 2, and so on until we hit number 8, which at that case, we would have 40 gallons per minute of water. So we would have to size our pipe based on 40 gallons per minute at the beginning of the line, and reducing the size of that pipe possibly all the way down to the size of pipe that you would require at head number 8, which could be 3/4 inch. So in this method here, your piping has to be large enough at the beginning to facilitate the maximum flow, and it has to continue down until you get to a comfortable place to reduce the size of it with your velocities. Say it's going 4, for example, or sprinkler head number 4, for example. We would have 1, 2, 3, 4, 5 sprinklers to be feeding up to there. So it would be 20 gallons per minute. So if at the beginning of the line we had 2-inch pipe, we may reduce it to 1.5 inches, 1.25 inches, and so on down the line. Zone number, or the good option for pipe sizing would be if you were feeding 8 heads, and you could split it this way, so you might break up the way that your field you were going to irrigate. But if you had fed 4 heads and split, again, I said it's best to feed from the middle. So you're feeding from the middle between 2 lateral lines, and we're taking half the flow going to each of the sets of 4 heads. Hence, the pipe sizing can be small. The best system, and it's the way that we aspire to design all of our systems, is the one at the top here. And in this case here, we have a central feed going through the 4 heads. So we're only feeding 2 heads in either direction in each of the laterals versus the 4. And we're feeding it this way. So the other real major advantage of doing it in this fashion is if each sprinkler head is still the same amount of water, your pipe sizing is going to be significantly smaller in this on the best option. Next slide. Okay, lateral friction loss. So here we're going along, and oh, look at that. It's the 5 gallons per minute we were talking about in the 40 gallons per minute. So here's that's going to show you how you would size each of your pipes out. You're looking at your friction losses. So to sprinkler head number 1, as is depicted on the picture of the left of the graph here. You're at that point there, the piece of pipe that's going over to there is 40 feet of distance. You're going to have 2-inch diameter pipe. You're going to be losing 0.69 pounds of pressure through that pipe. Friction loss of 4.48 for the whole 40 feet. And then as you go down to head number 2, sprinkler head number 2, our flow reduces to 35 gallons per minute. And as we could just follow that along, and our loss is going to be 0.54 pounds with a velocity of 3.6. And as we keep dropping down, we go the same until we hit head number 5, of which at that point we could drop to 1.5 inch pipe because our velocity is at a safe 3.6. And we're going to lose 0.78 pounds per 100 feet. And then we go, as I was saying, I'll go all the way down to head number 8, which is at 5 gallons per minute, and our loss is 1.25 with a velocity of 1.3, and so we're looking at using 1.25 inch pipe at that. In this case here, we could even be going smaller, but this is just for in this circumstance, perhaps our pressure is minimal. We have 50 psi. We can't afford to lose that much pressure. So in this case here, our loss is only going to be 9% of our starting pressure at that point. So that works well. Here we're looking at a calculation on fittings. So you've got a couple T's, T1, T2, and we can add the friction losses through those fittings. 8.8% is what our loss factor is on that. So we can calculate all that. The velocities are good, under 5 feet per second everywhere, as you can see. And we're using that, and as I talked about in the first picture here, we're using our best method, which is a central feed with a minimal amount of laterals going, distance going either way, smaller pipe going in all directions. And one thing I want to point out in this, the friction loss on this one here, at this best system here, with smaller pipe is 4.41 pounds. Friction loss. If you were to look at the other example that we did, I think you're going to find that your loss is very similar. But we're doing it with smaller pipe. the best option. So it just goes to show that there are a couple methods that can make a system work better and save you some money too. Okay, looped pipes. Loop pipes have the benefit of, if a lot of times I think the loops are done, sometimes it's a band-aid. Why is it a band-aid? It's because the main line was put in, it's too small, maybe on one side, and then if you were to put join the pipe up from another side, you can loop a main line, so that if you go to if you have one specific location where your water is flowing from, you were to tee from it, and you were to pipe around the perimeter of an area, you could use smaller piping. Why? Because the piping is looped, so the water is flowing in both directions to that one point, and with the loop system, you would, when you calculate out your losses, you're looking at half the flow to half the distance. So a loop system, the benefit of it is at any given place, not other than the elevation in a flat field, at any given place on a main line, you're going to have this. You're going to have fairly equal pressure because it's being fed from both sides. Loop system, very popular, used a lot in golf courses, large commercial fields, agricultural large projects are done that way, because you need different mains feeding from different areas in an agricultural project. So if you have an issue on one part of your main, you could isolate that out and get the water to it through the loop from a different direction. Better, and in this case here, we're looking at a looping, and we're looking at looping where we're feeding from one direction or feeding from two directions. So in this way here, we're feeding 40 gallons per minute all the way up. But if we were to be able to feed the water in both directions, you could minimize the flow going in any given place. On this one here, if it isn't always the best thing to loop a system, like I said, a lot of time, in a lot of circumstances in a loop system, you are looking at joining two pipes together that are going around the perimeter of an area. If the pipes are presently located that way, it isn't a bad idea to loop the main line to equalize the pressure. But if the piping, you were starting out from scratch, the central feed is still your best way to feed. You can see in this system here, we have a main line through the middle. The main line will be large enough to facilitate the 40 gallons per minute, and all of your lateral lines are going to be feeding off from the middle, so you're not going to have that extra piping that you would be putting in the loop system. Everything is going to be a good even distribution, all fed from the middle. So loops aren't always the answer, but there are times and places for it. One last thing I did want to mention about looping of a system is in circumstances on an electric system, for example, where you may have fast closing valves. Keep in mind that any given point on a loop, you have water flowing from both directions, and the piping, if it is too small, for a system, so like if you had, say, an 1.5-inch loop around a place, and it was being fed from a 2-inch service, let's say. So the 2-inch service gave you 55 gallons per minute of water, and you had the loop system in there of 1.5 inches, it would be marginal. In some circumstances, if you were to go to an 1.25-inch loop, for example, it would flow the water to that point and equalize your pressure because it's feeding from either side. But if you have a water hammer at any given point, because of the smaller pipe, if you have that volume of water being fed from either way, there is better opportunity for that pipe to incur some serious hammers and surges in it. So just wanted to point that out. Okay, here's my favorite picture, and Andrew has depicted amazingly for me. I've tried to do this with hand drawings for years, but anyway, I wanted to point this out. A lot of times in a situation where you are feeding from a valve and you are feeding through the valve with the maximum flow. So in this case here, we're looking at, say, 100 gallons per minute of water flowing through the system. your electric valve, whatever the size is, but let's say at 100 gallons per minute, you had a 2-inch valve, or you might have a 2-inch valve for that circumstance. A lot of times what people will do is they say, okay, well, from there, I'm going to run 2-inch pipe in either direction because I'm feeding from the middle. It's only 50 gallons per minute going either way. So the 2-inch T would allow me to go to 2-inch either side. Wrong. And I see this happen so many times. Where you're going to get the most hammer and surging on a system is at an intersection such as a T or an elbow or something like that. We want to equally distribute the water, 100 gallons per minute. You always want to put that through a large enough T to facilitate that entire flow. I realize that this T, where it's an intersection and half the flow is going either way, but that volume of water that's pounding down on the bottom of that T, 100 gallons per minute. If you had a 2-inch T, which I've seen so many times, what you're doing is you have a 2-inch T, which is undersized at that point. You have a hammer through a smaller opening that's going to cause you a challenge that is going to cause you a lot of broken pipes and fittings. If you put the 3-inch T in and bush it to your 2-inch on either side, you have the volume to facilitate this with the reduction to 2-inch after we've cleared the T. Thank you. Zone valves. Agriculturally, I think I'm seeing more and more systems going in right now with valves located above ground. From a service standpoint, and unless you're in a circumstance where you don't want to have pipes sticking out of the ground and you don't find that too appealing, then you would put it in a valve box. One of the big no-nos I see in valve boxes today is that if you're going to put a valve box in there, it should be centered in the middle of the box, and you should have ample room that you're going to be able to service that valve. If that valve is half under dirt, or it's jammed against the side so you can't get a wrench or a screwdriver in to undo your bolts, you're going to be frustrated, and you're going to end up digging that valve box up so that you can fix your valve. I've seen it so many times. If you're going to put a valve box in there, give yourself lots of room. But if you can live with it above ground, I see some major advantages to it. But in all circumstances, please note, in this plastic valves ahead of your electric valve. Why? If you have one zone valve go down on a system, and you have to shut your entire system off in order to fix that one valve, and it's in the peak heat of the season where you can't afford to not be irrigating your crops, then you have a problem. Put an isolation valve, very inexpensive. If you're on a 2-inch line, let's say, a 2-inch ball valve PVC one is less than $15. So it's $15 worth of insurance just ahead of your electric valve. It's going to allow you to be able to isolate that one valve, work on it at your own convenience, and then carry on with the rest of your system as is. On one picture, back one, please, Andrew, I didn't point out here, the one issue that you do see in valves above ground is a lot of times because you have a rise coming up, and depending on if you have too much of a rise coming up to your valve locations, sometimes you're going to be creating air locks into the system. So an air relief valve may be necessary on an above ground manifold to your valves. In situations, we've seen this before, this is a little battery controller that you can put in on a system if you don't have wiring or if you're retrofitting into a system. It's a good way to go. Automatic. Pressure reducing valves at various areas of your system, where they should be. Your pressure reducing valve maybe isn't always necessarily going to be on at the beginning of your system. Maybe you have a large drop in elevation, 60% of the way down your main line. That's the place you would want to have your pressure reducing valve in circumstances like that. Okay, thank you. Next one. This is just to show here a couple things here. And today I apologize for any confusion that we may have put forth with all the sizing up and down. Now, I'm going to throw one more curve at you. And that's the fact that electric valves for a couple of reasons, and any other size valves, a lot of times are undersized by one size over the size of your piping. Why do you do that? To save money, perhaps. The 5 feet per second rule for valves of brass or even electric valves, a lot of times is cheated on a little bit. Primarily why you can do that is an electric valve, especially if you go to a glass reinforced body or a brass bodied electric valve, they are going to be stronger, and the way that they're built, that your velocity, a lot of times you'll use 7.5 feet per second for sizing on a valve. So therefore, you can go a little bit smaller on your valve. So for example, let's look at that 2-inch pipe that you're putting in for your main line, and your zones are building around the 2-inch pipe. So you're going to have up to 60 gallons a minute, 55, 60 gallons per minute sizing of that pipe. We went to 2.5 inch on that one, but it was for a reason. You're going to see that 1.5-inch valve is got in the middle of your curve. If you looked at a graph for sizing of a valve, 60 gallons per minute would be in the middle of that curve. You could actually flow up to 90 gallons per minute through an 1.5-inch valve. Your velocity would be too high. But so that's why those valves are sized that way. Keep in mind one thing too, please, is if you oversize a valve, a lot of times you need some loss to go through an electric valve because of the spring involvement on it. So you end up having to throttle on the middle of the valve to put more pressure onto your diaphragm and your spring so that that valve will shut properly. Electric valves typically in a system should be shutting down in under 20 seconds. If they're shutting down in like 5 seconds or something like that, you're going to create a water hammer. But if a valve is too big, then a lot of times that valve won't shut for a minute. What does that do? That has an effect all the way down, a domino effect, so that if valve number 1 doesn't fully shut down, then valve number 2 doesn't fully open up. That could go all the way to valve 3. So none of your system is working properly. Keep that in mind. If you go to here you go on that, we're looking at the various flows, which we could go over at another time, but just to give you some ideas of a valve, 1.5-inch valve, they range from 80 to 150. Why is that? Because you can buy a plastic, strictly a PVC or ABS body valve. It's going to be less expensive, or you could go to the glass reinforced valve, which would be the 150 mark. These ones are all steel. Here's some Nelson series, for example, or aluminum. 3-inch 300, the approximate price of those, up to an 8-inch valve, 2,700 gallons per minute, $3,000 valve. Okay. So you should, today's big idea was you got to know your pressure everywhere in your system. You want to look at our friction losses. In order to maximize the efficiency of an irrigation system, you want to have your friction losses to be very consistent. So in order for that to happen, your pipe sizing, you have to have great care in taking the size of pipe that you require. You have to be cognizant of the flows and the distances that you're running. You have to know where your elevation changes are and how that's going to impact your system. Should you have an air relief valve in at that system? Too high pressures for a drip irrigation system are going to create a lot of havoc. Drip irrigation system, you only need 10 or 15 pounds of pressure. But still, you want to keep that in mind. Pressure reducing valves, obviously. A great tool to see what your pressure is at different locations is a pressure gauge with a little device called a pitot tube, which has got a little bent tube at the very bottom of it, which will insert into your nozzle on a sprinkler and give you pressure out in the field on the end of your wheel move or solid set irrigation system to see what your pressures are like, just to try and maximize our uniformity and pressure. Next session we have is going to be on emission design. So we're going to be continuing along the theme of designing. We're going to look at, we've got through the main line and how that goes about. I don't expect you today to have learned everything to the point where you would be sizing your pipe out. A lot of people such as Andrew or I would be more than happy to help you out with that. But we just wanted to give you a general idea of some of the reasons why you size pipes a certain way, how you would go about it, and the methodology in order to facilitate all this. So hopefully it's been helpful. that's all I have for you today on that. We're open for questions. Thank you.
Thank you very much, Bruce. That was fantastic. As usual, I just wanted to sit there and keep listening. We've used up most of the time we have allotted. There's about 5 minutes for questions. So one of the things I see in the chat here, and I'm going to take a stab at it first, and then maybe Bruce, you can tell me where I got it wrong, is where can you go to actually calculate out these pipe friction losses? Now, as Terry mentioned in the chat, the easiest and the obvious place to go is tables, just like the table we showed in the slide earlier. You go to a table, you figure out your pressure loss, and you literally just go one pipe to the next. If you're going down a lateral where you're losing all the way along, you just have to crunch it out. Now, I've set up some spreadsheets that I use for myself. There are equations that you can throw in that will calculate the friction. I'm happy to share my spreadsheet. I'll throw it in as an attachment to the email. There may be online calculators. My experience with them has always been dim. You pretty much want to think about each situation on its own and really go through the thought process of thinking where your flow is changing and how that's changing pressures each step of the way along. How do you go about these kind of calculations, Bruce?
I go utilize the friction losses, just as you say, in a drip system where you have multiple T's going on each rows. There is a factor, and if you look at the agricultural drip irrigation design booklet, it'll go over how you have a factor for each of your T's, and that factor, you can speed that process up on your laterals. Mainline, you should always do it in the fashion that we go about, utilizing the friction loss charts.
Now, I've seen your designs, and you do some beautiful hand-drawn designs, Bruce, but there's a question about whether there's any layout design programs you know of that you would use.
We did have some available when I was strictly in the supply and design business. Nelson put it out. They have a good design program software.
All right.
Look at that's more directed towards agriculture.
Somebody asked about the mapping. I use QGIS. It's online. It's free. It's a learning curve and a half. If you're in the region, the Kootenay Boundary region, give me a shout and I can talk to you about it. And maybe if there's enough interest, sure, we'll run a mapping session on it. But I just map it out, and then again, you go back to thinking about the system and making sure everything lines up from your source all the way to your emitter. And I think you must have answered all the questions as you went along, Bruce. I don't see any more coming in on the chat. But I will say there's probably been a lot to absorb. If there are questions that come up at any time, please feel free to send me an email. And if we can't get to your question in any one of these sessions, maybe we'll throw up a special session that's purely Q&A with Bruce here. Just looking to see if anybody else has come in. I think we're good, and it is 7:30 exactly, so that works out really well. Thanks again, Bruce, so much for all your knowledge with irrigation. Thank you also to our funders, the Climate and Agriculture Initiative BC, Columbia Basin Trust, and all of those other federal and British Columbia funding partners that support those programs, and the Kootenay Boundary Farm Advisors, which is supported by the regional districts of Kootenay Boundary, Central Kootenay, and East Kootenay. I am an advisor with the Kootenay Boundary Farm Advisors. You can, if you're in the region, call anytime. We're a free service, and we're just here to help farms however we can. Thanks again. And I see some more chat coming in, so I won't shut us down right away in case people want to copy that down or finish off. And yes, somebody mentioned Google Earth for sure. There's stuff out there. Maybe one day we'll geek out on mapping. Thank you so much again, Bruce.
Thank you.